So good evening, everybody. Hope all of you are doing fine and you're safe. Okay, so we had to miss last lecture due to certain commitments of mine. We'll try to cover those topics sometime in the future duration of the course. Let's say sometime during the weekday when you do not already have a scheduled lecture or towards the end of the course. So the topics that I was supposed to cover in the last lecture, those topics will leave for the future and we'll go as per the schedule. So for this particular lecture, we will study about what are the various synthesis techniques that are available to you as a research scientist. Okay, I thought it would be good to take up this particular lecture rather than the two that I was supposed to take, two topics that I was supposed to take in last lecture, because this is a very essential part of material science, to be able to synthesize something, to be able to create something, because ultimately that is the crux of the material, right? So starting with today's topic, I'm sorry. So this is synthesis methods in materials chemistry. Okay, why is it important at all? I mean, obviously, there's nothing to overemphasize this. Materials, as we have discussed right from the first lecture, are important to the development in the society of the society. Development of the society ultimately depends upon the advancement in materials and technology. And advancement would ultimately depend upon synthesis of new or improvised materials, right? I mean, there are so many concepts that if you can design a material like that, you can get those properties, or you can design a material like that, you can get this property. But ultimately, unless you are able to synthesize that material, that is not helping. So to be able to synthesize the material is the most important and the foremost criteria for advancement in materials and consequently society. So in fact, Dr. Tyagi also discussed in his introductory lecture that materials are so important that right from the prehistoric times, the identification of various periods is actually being done on the usage of material that was predominant or prevalent in that time, right? Starting from Stone Age, Bronze Age, iron, concrete, and right now we are in the Silicon Age. So there's so many materials that have actually changed the world over last few decades, starting from quasi crystal, high TC oxide, blue LEDs, and those are like they were so much important to the development of the advanced material that all of them have actually been awarded Nobel Prize in some time or other in last few decades. But behind everything, what is it that we need? We need synthesis of these materials in the desired crystal structure, in the desired overall structure, desired morphology, desired shape, and so on. So the various synthesis methods that are available to us are, excuse me. The various synthesis methods that are available to us are, as a material scientist, the first and foremost, or forget about material scientist, as a first method of synthesis, the man actually learned to synthesize something by mixing and heating them. And only the refined version of that is what we call as solid state synthesis or the ceramic method, or this is also called in a very crude terms among the material scientists as heat and beat method. Okay. Other than this, we have a battery of soft chemical methods, which includes your combustion synthesis, template synthesis, co-precipitation, sonochemical, hydrothermal, solvothermal, microwave. All of these are called soft chemical synthesis because they do not involve heating at higher temperature. Then there are several other refined methods, which are ion exchange. These are also called the derived methods. Intercalation, deintercalation, high pressure, vacuum heat treatment, and so on. And then once you synthesize the material, you need to process them as well, right? because ultimately to get it into usable form, I have made a powder, but I want to get it in a usable form. Suppose I want to, let's say, draw a circuit with whatever conducting material that I am, or the semiconductor material that I've synthesized. So for these, I need synthesis like techniques like inkjet printing, screen printing, spin coating, and nowadays, making polymers and polymer composite of our ceramics that we have synthesized. So all these are processing techniques that also fall under the broad category of synthesis method, though we would not be discussing them in today's lecture. Then there are various synthesis techniques which involve the biological species like bacteria or fungi or various other biological species or entities that help you to synthesize your nanomaterials. So they all come under what we call as biological route. Materials chemistry till recently involved conventional preparation method that would yield stable phases, and then those stable phases would have usual structure and normal dimensions. Okay, and ultimately, because everything would be just whatever is thermodynamically envisaged for that, so it will give usual properties. Now, what is the change that has come in this last few decades is now material scientists depend a lot on non-conventional preparation method, and they're actually bound by only the imagination. Once you know the concept, then mixing up two roots, finding a root which has been derived from 2-3 roots, and then designing and synthesizing your material is what we call as non-conventional preparation route. And because we are going by non-conventional methods, there is a possibility of getting metastable phases, which are not stable thermodynamically. They are not in the energy minima. And because you're getting metastable phases, obviously the structure they would have more often than not now will be the unusual structure, not the usual structure that you would predict for them. It is also possible to get nanostate. Then you can get tailored microstructure. What is tailored microstructure? People talk of nanofibers, nanorods, then various spherical morphologies, star-shaped morphologies. If you go to the literature, you would see them. And these tailored microstructure actually affect your electronic structure also. And there is a possibility to get tailored properties. So material chemistry, the more contemporary material chemistry insists on thinking out of the box. But when you want to do that, you also have to learn about what the different individual synthesis routes are, so that you can combine the characteristic of them to get what you want. Okay, so let us start with a very, very conventional method, which probably was started by probably the first synthetic chemist who would have done this, which is called the conventional solid state method synthesis. And I just told you it is also called heat and beat method. Why heat and beat method? Because ultimately you take the reactant, you mix them in something, mortar, pestle, ball mill, grinders, and then you heat them. So you beat them and you heat them, right? So this particular method is what I personally, as a synthetic chemist, completely rely on, because of the reliability of the products that you can obtain from this. So what it actually entails is that whatever compound you need, okay, you see what are the constituent elements, you choose the reactant accordingly, and then what you do is you weigh them stoichiometrically and then mix them thoroughly. That mixing can happen either by ball mill if the amount involved is large, or by your mortar and pestle. So that is called grinding. Once you have ground them, you pelletize them. Okay, we have something called the pelletizing machine, in which we make pellets out of them. Pellets are some kind of close packed bodies. Okay, and then once you have pelletized them, you heat them at required temperature for the longer duration. We will talk about these temperature and duration and how they should they be like. Once you've heated them, you record X-ray. Okay, and then you check for your product phase. The possibility is that the reaction has not happened. If the reaction has not happened, in that case, you will observe the XRD peaks due to reactants. If the reaction has happened, you will observe the XRD peaks due to product. Or if the reaction has happened incompletely, in that case, you will observe XRD peaks due to both reactant and product. So you go back to step number 1 in your flowchart, is that you again break those pellets, grind them for some duration, then again repelletize them and then heat them. Okay, so solid state synthesis is a multi-step process wherein you regrind, repelletize, reheat for 2, 3, 4, sometimes 5 and multi-steps to get your desired product. And then you also have to choose, you will use a furnace for heating. In that particular furnace, you will have to maintain an atmosphere. What is the atmosphere? Is whether you want the reducing condition, whether you want the oxidizing condition, whether you want the vacuum, and that atmosphere you will choose depending upon what product you desire, right? Crucible selection. What is crucible? Basically, the container in which you will keep your pellets or powder is a crucible. We'll talk about these points subsequently in next slides. But this is what basically happens in a conventional solid state synthesis. Example is, for example, I want to synthesize gadolinium zirconate. Okay. I told you in last few classes, this is A2V2O7 Pyruvate. GD2 ZR2O7. So what my reactants would be? Gadolinium oxide, zirconium oxide. So I will weigh because GD2O3 has already got 2 atoms of gadolinium in GD2O3, but I need 2 atoms of zirconium in my GD2ZR2O7, but ZrO2 has got only 1 atom of zirconium. So I will have to see, okay? I will have to, for every 1 mole of GD2O3 that I am weighing, I have to weigh 2 moles of ZrO2 to get GD2ZR2O7. This is what I meant when I said that you have to weigh stoichiometric amount of solid reactants. Okay. Similarly, LaCrO3. Now, La and Cr in this particular compound are in the ratio of 1:1. And the natural reactant which will come to my mind if I know that I have to synthesize LaCrO3 are La2O3 and Cr2O3. But fortunately, La2O3 has got 2 atoms of lanthanum in 1 formula unit. Cr2O3 has got 2 atoms of chromium in 1 formula unit. That means 1:1. So now, when I weigh my reactants for synthesizing LaCrO3, I will take them in 1:1 ratio. 1 lanthanum oxide is to 1 chromium oxide to get 1 LaCrO3. All right. But one thing that I must tell you, and that obviously you would have guessed also, because solid state synthesis, it involves a multi-step process and heating at high temperature. Okay, so it will give you only what are thermodynamically stable product. Whatever thermodynamics will judge for these particular reactants, ये दोनों मिलाओगे तो आपको ये मिलेगा. Okay, whatever by energetics, whatever is feasible for that combination of reactants is what you will get. So solid state synthesis gives you thermodynamically stable product. Okay, now we talked about we'll do this and that. So what are the tools of solid state synthesis? I generally, what I do is I grind my reactants in these kind of material containers, which you also know are called mortar and pestle. Okay. If you want to grind it in larger quantities, like in mortar and pestle, you can grind up to 5 to 6 grams. More than that, not that it is not possible. You get larger size of mortar also. The only problem that happens is when you do manual grinding, it is not very efficient. So for larger batch size, we go for ball mill. Now, what is a ball mill? It is basically a container that has got zirconia ball. You put your powders in it, and that is put on a station which rotates. Okay. So because of rotation, these balls move up and down and your powder gets mixed thoroughly. That is why it is called ball mill. It mills your material or grinds your material with the help of action of various balls. Okay. For heating, then grinding is followed by pelletizing. I've not shown a pelletizing machine here. Heating, then pelletizing is followed by heating, and heating is done in furnaces. Furnaces are mostly, there are many types of furnaces, but we classify them into two classes. First is muffle furnace. Muffle is whatever I have shown here. These are the box type furnace, okay? It's like your OTGs and microwave, okay? This is how they look like in shape. And then you can also have tubular furnace. Tubular furnace have got a shape of the tube. They have an alumina tube. And in general, we use muffle furnace when we want to synthesize many pellets at one go. Because here the volume of this heating zone that you can see inside is large. Tubular furnace, what we call as the heating zone is very small, and you cannot really go for many reactants, many powders or many pellets at one go. Okay. So these are of course the die and plunger machine with which you make pellets. This is not exactly the pelletizing machine, but the die and plunger. So these are the dies. They've got grooves here, as you can see. So what we do is we put the powder in it. We put this pelletizing rod on top of it and then press it with the help of the pelletizing machine. And you get pellets like you have your medicine tablets. Okay. So they are generally made up of tungsten carbide. Now, factors affecting solid state reaction. Once I know, okay, before that, let me just show you the schematics, because then you would be able to easily understand what are the factors that affect solid state reaction, or in other words, what are the things, what are the keys that I can, control to tune my solid state synthesis. Okay, so what happens in solid state reaction? Basically, assume these pink balls are your reactant A, blue are reactant B, and they're powders. And I've magnified them, assume they're very small particle. When I grind them, they will look something like this. I mean, they're kind of homogenized. Now you heat them, and let me tell you that solid state reactions are diffusion control. When I say diffusion control, A particle will move towards B particle to form C, which is the product that I want. The C is now this dark pink color particle. And all of you know that for solids, it is very difficult to, solid atoms, it is very difficult to diffuse towards each other. That is a very, very slow process. Okay. So what will happen is let's assume these are A particle and these are B particles, and they are diffusing towards each other to give you C. But what happens is, as the C product wallet goes on increasing, let's say in this direction and in this direction, it will become progressively difficult for B to go towards A and for A to go towards B. Okay, so that is why at one particular point, आप कितनी भी देर उसको heat करोगे, the reaction will not proceed forward. So I will have to, this is where your regrinding comes into picture. As I told you, that solid state process is a multi-step process where you have to regrind, repelletize, reheat. All right. So we repeatedly grind and heat it till we get homogeneous C product. Now I know how it happens. So now let me see what are the factors that affect solid state reaction. Temperature, because it is diffusion control. Unless you raise the temperature, the solid atoms will not move from their lattice site. Okay. Duration of heating, कितनी देर मुझे उसको heat करना है. Most of the time, this particular factor, it comes by experience. Okay. Nature and chemical form of reactants. We will talk about each of these factors. Area of contact between reactants. But if you understood the schematic that I told you in the last slide, you will be able to appreciate each of these factors. Then heating and cooling rate. Okay, like the rate at which I'm heating and cooling it. Okay, now selecting the reaction temperature. First and foremost, all of us agree without me having to read that solid state reaction have to occur at high temperature because they need energy to diffuse. Otherwise, why would they go towards each other and react? So first and foremost, what we do is we compile the melting temperature, decomposition temperature, etc. of the reactants. Okay. Now, there have been two laws which have been given to give you a guideline to choose the melting temperature, though they are not hard and fast. Most of the time, these things come by experience. But still, to give you a starting point, one of the rule is Taman's law and the other is head wall effect. So what does Taman law state? That diffusion of ions in any lattice, it becomes substantial. It becomes enhanced at when the temperature is 0.5 to 0.7 times of your melting temperature. Okay, or in other words, 2 by 3 times of your melting temperature. Okay, that means what does it say is that now basically why I'm looking at it. I want my reactant A and B to become sufficiently mobile so that they go towards each other and react, right? So for that, I want them to become loosely bound. So what it says that the diffusion of the ions in the lattice is substantial when the temperature reaches 2 by 3rd of melting point of any solid. And head wall effect state that reactivity of any solid, okay, it increases considerably in the vicinity of the phase transition, if at all your reactant is undergoing phase transition. Okay, so what we do is, when I start planning my synthesis, I look at my reactants, I compile their melting temperature, then I see which is the lowest melting reactant. And my first heating temperature, as I told you, it's a multi-step process. My first heating temperature, heating step has got temperature which is anywhere between 0.5 to 0.7 times of the melting point of lowest melting reactant. Okay, whatever reactant melts at a lower temperature, I take 50% to 70% of its melting temperature, and that I choose as my first heating temperature. So this was about selecting the reaction temperature. Now, area of contact between the reactants. Now, what does that mean? More the surface area of your reactant A and B particle, more you will be able to mix them together nicely, more they would be, more their surfaces are in touch with each other. That is, they have a higher is their area of contact, better would be the diffusion, better would be the reaction. Okay, so what does grinding do for us? Grinding increases the surface area of the reactant. Okay, when the surface area of individual reactants are increased, that also increases the area of contact between them, and that helps in better diffusion. Okay. Pelletizing, what it does is, again, now when you pelletize it, when we pelletize it, we apply a large pressure on it. So the pressure applied during the pelletization again increases the area of the contact, enhances reaction, and it also increases green density. Now, what is green density? Green density means you have simply pelletized your pellet by applying pressure. You have not heated it at all. Okay, that is called green density. And if you have better green density, then when you heat it, you will have higher density and you will get better sintered bodies. Okay. Then regrinding and repelletizing. What do they do? They do the same purpose. They break your product layer and increase the surface area of the particles and hence increase the area of contact between unreacted A and B. Okay. Now, there are so many methods by which, this is where the solid state chemist applies his mind. Okay. There was a question. Sorry. Melting temperature will be different for different precursors if we are using 2,3 composition. Select the compound precursor. Shrikant, what I want to say is, suppose I am making a product ABC by mixing A plus B plus C. Okay. In that case, your melting point, you will choose whichever reactant out of A, B, and C will have lowest melting and 50 to 70% of melting point of that. Now, if I understand your question, is this what you wanted to ask or something else? Precursor means, like suppose you're using carbonate of A or nitrate of A or this of C, or you're satisfied by what I replied? Okay, great. Fine. In that case, now what are the different ways by which I can, first was grinding and pelletizing. Okay. Now, sometime what happens is, I'll give you an example and then we talk about it. Suppose I want to synthesize, if you remember, we studied the structure of this particular compound. This is my 1,2,3 oxide, superconductor. I want to synthesize this. Now you look at it, what are the reactants that you can think of? Y2O3, barium oxide, copper oxide. All right. This is one way by which you can synthesize it. But instead of barium oxide, my material scientist instinct tell me to go for barium carbonate. Why? You know what happens? Barium carbonate, with carbonates and all, we give first the heating at lower temperature. Let's say simply at 600 to 700, depending on the decomposition temperature of your carbonate. So what happens is, this barium carbonate will in situ decompose first into oxide. So before reacting, it will decompose into barium oxide and CO2. Okay, and this in situ form barium oxide, it is very fine grained, and because it's fine grained, it has high surface area, and because it immediately bana hai, it has just formed, it is highly reactive. It has high surface area and it has higher reactivity. You know, so because of high reactivity of this reaction will now proceed faster, giving you more homogenized products. Okay, so the choice of the reactant, the choice was fine. Anyway, you use barium oxide. Either you started with barium oxide or you use barium carbonate. जो आपका ultimately react किया वो barium oxide ही था. But barium oxide मैंने कैसे produce किया? How did I produce it? Changed the reactivity and hence affect my synthesis. Okay. So this was in situ decomposition. अब मुझे पता चल गया that this is possible, right? But for many reactant, like for yttrium oxide, I will never go for yttrium carbonate. तो फिर मैं क्या कर सकती हूँ? Ultimately, what barium carbonate का जो in situ decomposition हुआ, what did it do is it produced nano-sized barium oxide. So my instinct would be, okay, let me start with nano-sized reactants. Na? There are many easy processes by which you can produce nano oxide. And this is simply producing nano oxide. I don't want any desired morphology. I don't want to go for fancy route. Simply take nano oxide reactant, nano-sized reactant, and do the solid state of them. Surface area is higher. The temperature that you need would be lower. The time duration would be lesser. And you will get a product in lesser number of steps as would otherwise be required with the micron size or the bulk size reactant. Okay. So I hope this is clear. Nature of the reactant. Okay, again talking about the other parts of nature of reactant. One of the very first mistakes that I did when I was doing solid state synthesis in my initial 2-3 years was I was preparing some compound with terbium. Okay, and most terbium is a rare earth oxide. You know, it's a lanthanide. Now most of the rare earth oxide actually have general formula M2O3, lanthanum oxide and Nd2O3 and dysprosium oxide, gadolinium oxide. So I thought maybe terbium also has that particular composition. I did the calculation accordingly. but I didn't get the product. Why? Because later on I realized that terbium oxide actually, most of the time, the bottle I had, uska nominal composition was, uska formula was TB407 and not TB203. So this changed my calculation. Okay. So you have to be very sure what reactant are you taking when you're doing calculation. All right. And in or another corollary of this is that you should choose only that reactant, because for any element that you're choosing the reactant, choose only that oxide of that, because for let's say multivalent elements you can have it's uska monooxide or dioxide or whatever. Choose only that oxide which you know will have well defined composition, so that your calculations do not go wrong. A. Second, many of our oxides are hygroscopic. Okay, हो जाते हैं, especially in places where you have lot of rains, like in Mumbai. Your materials absorb water molecules, or otherwise over a period of time they absorb gas molecule. So do gravimetry before you start your reaction. Gravimetry means, let's say I've taken my oxide, heated it at 5, 700, 800. तब तक it will, if it has absorbed any water molecule, because adsorbed water molecule easily go off at lower temperature, then whatever suppose you started with 1 gram of it, and after 700 ka heating you are left with 700 mg. So you can easily relate that 300 mg was nothing but your adsorbed impurities. Now you would know that if you're starting with 1 gram of your oxide that is in the bottle, actually uska only 700 is effective. So you can calculate accordingly. So that is the reason you have to know, you have to do the gravimetry, especially when you know that these kind of material have the tendency to absorb water molecule or gases or other species. Okay. And otherwise, after this gravimetry, in spite of this gravimetry, I make it a point, and every good synthetic scientist should make it a point, that whenever you are starting your synthesis, okay, because it goes without saying that it will have, if not in large quantity for which you need gravimetry, to some small extent, your material will have occluded water or CO2 or other things. So preheat your reactants. Always preheat your reactant. And that need not be done at very high temperature. For example, the rare earth oxide, all of them have their melting point close to, let's say, 1800 and beyond. Do the preheating at 800 degree for 6 to 8 hours. Okay, and then preheating of the entire amount of sample that you're going to use. So you would know that exactly you are starting with the pure material, and at what temperature you need to do preheating. उसका एक TG scan लगाओ और thermogravimetry करो. It will show you कि कहाँ पर your adsorbed impurities are completely gone. उसके बाद it will become completely static. So that particular temperature you choose as a preheating temperature. All right. Again, this is, as I said, it is very advantageous to use carbonates and acetates, because heating them at certain lower temperature in your reaction mixture will actually give you in situ production of nano-grained reactant. But you also have to be very, very cautious that when you use acetate, carbonate, nitrate, oxalate, which are prone to, which actually would decompose and give oxide as your reactant. But you have to make sure that you heat, suppose your first heating temperature you've calculated as 1200 by that Taman rule or whatever. Before that, make sure that you heat, if you are choosing one of these reactant in one of these form, heat it at 600 to 700, so that the decomposition happens at a lower temperature. Because if you heat it directly at 1200 and 1300, it will decompose in a very violent manner. Violent, not it will cause any accident, that won't happen, but it would spill over your reaction mixture. Okay, and then your composition will be disturbed. So temperature profile means I started with my room temperature, and there is a possibility to do that in a programmed for programmed temperature furnaces. You can actually give it that it should take it to this temperature, heat for 3 hours, stay there for 3 hours, then raise it to this particular temperature and so on. So temperature profiling has to be chosen very wisely to avoid any spillage and decomposition. All right, now everything fine. You will have to keep your pellets in something, right? So that crucible ka jo material selection hai, that is also very essential. And what will it depend upon? It will depend upon synthesis temperature, because your crucible material has to be stable at that temperature, right? उसका काम और कुछ नहीं है, just has to hold your reactant. So it should itself be stable. Nature of the reactant. It should not be reactive. It should not undergo any reaction of sort with your material. I myself have lost many material because of this, because my reactant would react with my crucible material. And then cost. Suppose you are doing some very, very high-end synthesis, then you would not bother about cost. But most of the time, these alumina boards, platinum boards that we use are costly. So we have to use them wisely, okay? And there are so many crucible materials that are available. Porcelain, quartz, gold and silver, platinum, alumina, magnesia yttria, graphite, and so on. What will I choose has to depend upon, as I told you, the temperature of its stability, and we have to keep under consideration its compatibilities and incompatibilities. Taking three example, most often which you will probably use as a solid state scientist. Quartz we use only if we have to do synthesis up to 900. But then you have to take care that they are reactive with metal fluorides and alkali metal. Okay, if you have these, don't use quartz. Platinum crucible, very, very reliable crucible. You can go up to 1400 with them, but after that the platinum starts becoming softened. But make sure that you're not using bismuth, lead, cobalt-based compounds and metals. All right. Alumina. Alumina is what we use regularly, day in and day out. You can use them up to 1800. Beyond that, very, very rarely only you go for any synthesis. But the only thing is you cannot use them with fluoride. You can use for all the other things up to 1800, but not fluoride. Okay, so and you want to go to super high temperature, for example above 2000, then these are the material of choice for you. Magnesia, yttria, thoria, YSZ, all of them have got melting point beyond 2400. Okay, then graphite you can use even above 2500, but you have to make sure that you use it in vacuum. If you don't use it in vacuum, it's after all carbon, it will become CO2. Okay. So this is save this slide for future use. It's a very, very important slide. Gives you a guidelines about the kind of crucibles that you should be employed. All right. Control of atmosphere. How is that important? If I want to synthesize a compound, like we discussed about LiFePO4, the cathode for lithium-ion batteries, I want iron in +2 form. Iron in +2 form. And we know that iron has the tendency, मैं उसको थोड़ा भी temperature पे heat करूँगी, in normal static air, normal atmosphere, it will go to Fe3+. That means if I want to retain my Fe2+, I have to have reducing atmosphere. If I am not able to maintain reducing atmosphere, at least vacuum. Okay. If I want higher oxidation state of a particular element in my compound, I'll go for oxidizing atmosphere. Then we also have to choose whether I want static air or I want flowing atmosphere. Like in my tube, on one end I put the gas nozzle, the gas is going on this side and the other side it's going out. Or I simply flush my system and then block the tube and then heat it. That's static. Okay. And then sometimes what happens is you want to make fluoride. In that case, my atmosphere itself only contains of one of reactant. So I can have reactive atmosphere, which is fluorine, HF, etc. So depending on the reactants that you're using, depending on the products that you want, we choose our atmosphere. And then static air is nothing but, flowing gas for your, if you are maintaining, reducing or oxidizing, static air is what we generally do. Furnace में मैंने रख दिया, furnace band hai, I have not maintained any special condition. We call it static air atmosphere. Okay, fine. The preparation of moisture sensitive, I'll just take one example. This was one of the earliest synthesis that I did. We wanted to make metal fluorides and especially solid solution of calcium fluoride and NDF3. Okay. Now fluorides are moisture sensitive and air sensitive. I cannot heat them in furnaces as such. So what we did is we ground them, made the pellet of them. Okay. Those pellets were wrapped up in platinum foils. Okay. And then this is shown as tube, but it was simply wrapped up. Like you have your aluminium foil, a simple foil kind of thing. Wrap it in this. Then what we did is we took one quartz tube. उस quartz tube के अंदर we put my this thing, the foil. And then उस quartz tube में we created a vacuum. Once the vacuum was created, it was using a torch, the torch basically, with which you seal the glasses. That glass, this quartz ampule, it's a quartz ampule. It was sealed and cut off from the main gas line and sealed here. Now it has vacuum inside and it has my platinum ampule which is containing my reactant pellet. And this quartz tube entirely, this total quartz tube went into the furnace. Okay. Now I did not have to maintain my furnace in under any special atmosphere because the atmosphere in this tube is now vacuum. And then we heated it at 900 and we got metal fluorides. Okay. So this is how we plan our synthesis. Now, okay, now there are various variations to solid state synthesis. Like in solid state synthesis, when I heat it in furnaces, I am providing heat by an external source. Now there is something called spark plasma assisted solid state synthesis. Now this process is not available in your next door lab everywhere, but it is available anyway at many places. In BRC also we have it. Now here what happens is, this is the schematic of the setup. Okay, so what happens is, here the concept is you are applying pressure from both the sides on your reactant powder and a current. Now what does that current do? Okay, so these are your pressure, hydraulic press from both the sides, biaxial press. You apply the pressure so that the pressure is applied on the powder and the reactants become close together. And this is a graphite dye. Okay, it is shown here, but it is covering your powder. And then graphite is conducting, you apply current on that. Okay, that's DC voltage. So what happens is, it conducts current, and if your powder is also conducting, it will also conduct. Then by Joule heating, that when the current will pass, then due to Joule heating, the temperature would be risen. Okay, that means the high temperatures are produced, are applied not externally like we do in our furnace, but internally. We are passing the current, and by heating, Joule heating, the heating is happening, and depending on the conductivity of your material, the temperature would be risen. So basically, it is applying both pressure and heat simultaneously. That carries out the reaction for Joule. Okay, so what are the characteristics? It is internal heating by Joule effect by pulse direct current. You have very fast heating rate because immediately it is produced, and very fast cooling rate. Simultaneously, along with that current, we are also applying uniaxial. It's not biaxial, sorry. It's a uniaxial in one axis. Biaxial is if I have along Z direction and one more direction, X or Y. That is biaxial. We apply uniaxial pressure. So what it leads to? Better contact between the grain of the reactant, shorter time duration, and it controls the grain growth. What is the best part of this synthesis, Now suppose I have made the product and I want to make my product as a highly dense bodies, which is very important because sometimes we do not desire porosity at all. Now when you go by solid state method, the max density that you can achieve is 80 to 85%. That is the drawback of solid state synthesis. Sometimes we want very high density, and any other method of increasing density actually does it by grain growth. I talked, if you remember, when we were doing 2D defects, we said that, the grain boundary annihilation happens by coalescing of grain. More and more chota grain they join together, they form bigger grains. And this is how density increases. But sometime I want that my nano size should be retained. I don't want any grain growth at all. And I also want densification. This is what is precisely achieved by your spark plasma assisted synthesis. Okay. In fact, spark plasma assisted solid state synthesis has come only later. Ultimately, initially, spark plasma has been developed for obtaining highly densified objects. So it minimizes grain growth, shorter duration. You do not need any external heating, and hence there is lesser power consumption. Microwave solid state synthesis. Again, it is solid state, but how are you providing energy? By using microwave. So, अभी इसका condition क्या है? मैंने दोनों reactant mix करके रख दिए, like I do in my solid state. But now one or more of my reactant should be microwave absorber. Okay. So what will happen is when I pass microwave through it, they will absorb microwave, heat up, the temperature would be risen and the reaction would happen. Best part about it is very fast heating and cooling it. Why? Because you can control it by putting microwave on and off. Microwave on, the temperature rises. Microwave off, temperature cools down. Okay. Again, advantage. One of the advantages, see, anything that you do very fast, like when the heating and cooling rates are very fast, the possibility that it is not going by your thermodynamically driven route or pathway is very high. In that case, there is a possibility that you might land with the product which is metastable, which is actually not stable by thermodynamically consideration, but it has been made kinetically stable क्योंकि वो एक लोकल एनर्जी मिनिमा में गया और एब्सोल्यूट मिनिमा में आने के लिए आपने उसको टाइम ही नहीं दिया एंड इट हैज गॉट ट्रैप्ड. Okay, and these kind of phases when you obtain, they can be very interesting. Okay, and then advantages, for example, if I want to make silicon carbide from silica by carbothermic reduction by high temperature solid state route, it is multi-step, it is highly energy intensive. You use microwave, you can heat it at 1300 and only in 5 minutes. Saves you a lot of power. Okay, so these are some variations only in terms of how you are heating your solid state mixture. All right. Now the problem with your heat and beat method is, solid state method is, reaction is diffusion limited. तभी आपको ज्यादा टेम्परेचर चाहिए होता है, तभी आपको मल्टी स्टेप करना होता है. Then it may give you incomplete reaction, so you have to do multi step. Then many a times the product layer may become so much thickened that you might not get a homogeneous product. So compositionally आपको inhomogeneous product मिलता है. इसका मतलब क्या है? Suppose I want something called A2B3. तो most of the time मुझे A2B3 मिला है, लेकिन कहीं कहीं पे AB2 मिला है. So it has both A and B, but they are compositionally inhomogeneous. Okay. And in solid state, there is little chance of kinetic control. Metastable product कभी मिलेगा ही, very rarely मिलेगा. Okay. And you will not get desired microstructure. As you say, as I told you, density max जो आप जा पाओगे would be 80 to 85%. तो अभी मेरे पास solution क्या है? These were my problems. What are the solution? You have to decrease the diffusion distance between the reactant. Incorporate in some same solid precursor, na? Maybe that would help. Or do something that causes intimate mixing of cations. Okay. Performing reaction in molten flux. Or your other choice is go by one of many soft chemical synthesis. So let us see some of them. Okay, we'll take a 2 minutes break. I'll have some water. You think about what you did not understand, and we go to second part of the lecture. Slides. Okay. One of the simple variation to your solid state synthesis is by precursor rule. So what we do is we choose a path. Suppose I want to make zinc ferrite. So what I start with, I choose a reactant of both zinc and iron, which is similar in nature, and there's a possibility of them forming a complex. For example, I choose iron oxalate, I choose zinc oxalate. This is called precursor rule. That is, what is important here is the choice of precursor, here oxalate. Okay, you both of them are soluble in water, they're oxalates, and then slowly evaporate. They will complex together to give you, and mind you, the stoichiometry has to be maintained. Fortunately for us here, every oxalate I want to make ZnFe2O4, where I have for every zinc atom I have 2 iron, and fortunately for us in oxalates, iron is Fe2 oxalate and zinc is monooxalate, right? So now I choose this, okay, and when you evaporate it, it dries up and it gives you a complex of this form, a hydrated complex. Okay. Now this hydrated complex, you heat it at higher temperature. You will be left with your desired product and the gaseous molecule. Okay. So what did you achieve by this? You achieved a complex where both your reactant, iron and zinc, are in highly close proximity because they are together almost on the closer together almost on the atomic level. A particular molecule may they are present in the same stoichiometry that you want in your product. Okay, that is why it is called precursor method. You have made a precursor to your desired product. Okay, so how do we do? We mix the starting reagent together in the solution, remove the solvent, it will leave behind an amorphous or nanocrystalline mixture, and in one of the reactants such as which are easier to decompose later on, such as acetate, citrate, oxalate, alkoxide, and then you heat the resulting precipitate to induce reaction to get the desired product. Fine, very nice. Now this is every synthesis method I will try to validate by some of the synthesis that I've done by my hands. Okay, if possible, if I've done that particular thing. Like once we synthesized this cerium vanadate and I wanted to substitute moly in them. I wanted to develop some Cheap lead sorbents. Lead, all of us know, is a toxic species that is present in the water at many places in India. So what I did is I chose cerium nitrate. Okay, I chose ammonium vanadate. Then I chose ammonium molybdate. Mix them nicely and let it dry at 100 degrees centigrade. Okay, and then you let it heat at 90 to 100 degrees centigrade for a long time. You'll get a precipitate. Okay, that particular precipitate you filter it and wash repeatedly to remove. Why? Because the product has cerium, the product has vanadium, the product has moly. So the other reactant that is present in my mixture is uh, ammonium nitrate. And that would be soluble. Okay. So if you wash it repeatedly, ammonium nitrate will be gone and you will be left with this particular precipitate. In my case, I was lucky that I directly got this particular thing. I did not have to heat it like this particular thing to obtain my final product. But heating and all we call them the post-synthetic process, and sometimes they are necessary, sometimes they are not. Okay, so this gave me my product. This is of course the XRDs, and we did the TEM, and then it gave us a very good lead sorbent which could take up 100 milligram of lead per gram of this material, and in as small as 10 minutes. Okay, so a very simple synthesis. I think this would probably the simplest synthesis possible, which is also called precursor synthesis or the co-precipitation, where you simply take the reactants, the salts of two reactants that you want, mix them, precipitate them. Either they will precipitate by themselves, like in this particular reaction, or you add hydroxide, they will form a hydroxide. You take it, heat it, it will form oxide. So this is the simplest process that is possible. Okay, advantages super easy, absolutely no fuss. Rapid synthesis, low temperature. What you're heating it at 80, 90, 100 so that the reaction could go to completion. That is it. Control over composition because you know what you're mixing there, right? Limitations इसकी क्या है? Limitations ये है कि पहले आपको दोनों को solubilize करना है, वो जरूरी है. Solubility comparable होनी चाहिए, otherwise from your side, you have weighed stoichiometrically and dissolved them, but they did not have comparable solubility. So the stoichiometry would be lost, right? Okay. Then they should not have different precipitation rule. अगर A ज़्यादा precipitate हो रहा है, B कम हो रहा है, then again you wanted to have a A to B stoichiometry in your product, that would be lost, right? Then howsoever hard you try, trace impurities also get precipitated. द एप्लीकेशन आप जो देख रहे हो बाद में अपने प्रोडक्ट की, अगर वहां पे ट्रेस इम्प्योरिटी से फर्क नहीं पड़ता है, टोटली फाइन. अगर पड़ता है देन यू विल हैव टू रीथिंक बिफोर चूजिंग दिस पर्टिकुलर मेथड. Then there is no control over particle size. That is true. Then possibility particle size homogeneous नहीं होगा. Homogeneous का क्या मतलब है? Suppose I am getting all my particles from 15 nanometer to 20 nanometer. That is homogeneous. But if my particle size varies from 5 nanometer to 100 nanometer, I call it heterogeneous particle size. That might happen. And sometimes batch to batch reproducibility issues are there because it's a very simple process, you know. So these kind of issues are associated. Again, look at your application. If your application is very high end, then refine your process. Otherwise, try to go by the simplest process possible. Sol gel. Most of you would have heard about it. Here what we do is we dissolve our precursors, whatever precursors we have, mostly alkoxide. Sol gel may we use organic precursors. Alkoxides are used. Alkoxides of the metal ion that you want in your product. Dissolve them, okay, and then hydrolyze them. They will form a hydroxide, which is called a salt. And then you that undergoes condensation, and after condensation, it forms a gel-like thing. that gel is left to age to give you a three-dimensional network, and then that gel is heated to give you your oxide product. Okay, again showing it to you. Suppose you want a product which has these 1, 2, 3, 4, and 5 species. You want an oxide. You start with alkoxide of all these, okay, given in the first box. Mix them together, they will undergo complexation, okay, then hydrolyze them. How does hydrolysis happen? We add few drops of water, or water is already there. This is how hydrolysis occurs. So you get MOH. Okay. Then what will happen is they will undergo condensation. And what is that condensation? Your MOH, where M could be any of these ions, will combine with another MOH or MOX, where X could be your alkoxide. We talked about OR. They will undergo polycondensation. Condensation में क्या होगा? This XOH will be removed and you will have MOM linkages. You will have three-dimensional MOM linkages, center it, and you will get the product. Best part about this synthesis route, there are very few routes in which you want to have multi-elemental product और वो उसी स्टोइकियोमेट्री में आपको बनाना है और बल्क में बनाना है. There are very few routes which can ascertain that. With Sol-Gel method, multi-elemental composition can be made with good compositional control. Okay. So methodology, I've already told you, you mix the raw material, you carry out hydrolysis, polycondensation, so that you get a sol. Okay. Then this colloidal particle will slowly aggregate after aging of sols, and they will form gel, which is a 3D network, and you dry your gel and you sinter your gel, then you can get materials with different microstructure, and even nanostructures are possible. And this particular thing will depend upon how you maneuver your drying and sintering process. Okay. Parameters that affect your product properties, especially in case of sol-gel synthesis, is the rate, how fast you are carrying out your hydrolysis and condensation. Slower and controlled hydrolysis will get you smaller particle size. Okay, these are some of the parameters that you need to learn to control, and eventually everybody does. Once you have done that process 2, 3, 4 times in your lab, handled it yourself, done a lot of troubleshooting, you get to know these things, and these things come by experience. Advantages, as I told you, that since your starting material are in the molecular level, I mean, they are mixed up in the same gel, okay, final products are homogeneous. Relatively high in purity, और कोई composition बनने का possibility ही नहीं रहती है. Then synthesis is done at appreciably lower temperature as compared to your solid state route. Okay, it allows for the fine control of product chemical composition and specially suitable for preparing multi-component materials, as I told you. Limitation, you have organic solvents which are costly, and relatively, of course, you would want to handle aqueous product as much as possible. ये एक drawback है, and reaction time is relatively longer, right? Next is hydrothermal synthesis. What does it tell you? The two words itself, hydro and thermal. Hydro means aqueous, thermal means heating. So basically, hydrothermal methods of synthesis involve performing a reaction in aqueous medium at temperature above 100 and pressure above normal. That is above 1 bar. Okay. और उसी hydrothermal में अगर आप water की जगह पे, aqueous medium की जगह पे I use a non-aqueous solvent, I call it solvothermal. Okay. So when do we need hydrothermal synthesis? When we want to grow crystal defect-free material. Okay, hydrothermal synthesis is what actually happens in your earth crust. You have high temperatures and you have aqueous medium. So whatever natural minerals that are grown in the earth crust are grown by hydrothermal process. And you want to grow layered material because layered material, most of them are not stable at high temperature. उसके लिए आपको low temperature route चाहिए ही चाहिए. When I say low temperature, hydrothermal can be classified as relatively low temperature because we do not go beyond 200, 300. Okay, like 200 upper max. Whatever hydrothermal I have used, I don't go beyond 160 to 180. Microporous material, nanowires. That is, if you want to have some specific shape of the material, nanotubes, nanowires, similarly. So, what is the role of water? We'll come to that later. What is hydrothermal? It is basically how you prepare food in a pressure cooker. Okay, you fill your pressure cooker with your reactants, and then it is heated. Pressure is produced, which cooks your food. The only thing is, in pressure cooker you have a vessel that gives off the pressure. In our hydrothermal, we maintain that pressure. Okay, so ultimately what is happening is you are providing it an external temperature which is not very high, and it has an autogeneously created pressure. And where does that autogeneous pressure come from? By vaporization of your solvent, which is your solvent, alcohol when you are doing solvothermal, water when you are doing hydrothermal. And how much pressure has been generated, that also you can decide, because ultimately what will pressure depend upon? How much you have filled your box, the autoclave. Okay, कुकर प्रेशर कुकर में आप कितना भरते हो उसी पे डिपेंड करता है प्रेशर कितना डेवलप होगा. एंड यानी योर फिल्ड वॉल्यूम and your external heating temperature controls your pressure. And there is a well defined graph that is given in the textbook that gives the relation between filled volume of the autoclave and the pressure generated at any given temperature. All right. So this is a synthesis under ambient temperature, high autogeneously generated pressure. Nowadays, the hydrothermal instrument that come, the one that I have in my lab, there is also a pressure provision that in addition to this autogeneous pressure that is being generated, I can exert an external pressure. And how do I do that? My autoclave has got a vent which I connect to the gas cylinder. And then any inert gas, argon, nitrogen, basically it will not react with my reactants, but it will just go and accumulate, which creates the pressure on my reaction system. All right. So how do we do it? We take salts of my reactant, and best part of the hydrothermal is that they need not be completely soluble. One of them is completely soluble, the other is not. Both of them are partially soluble, even that is done. Because that work your water does. So water, what it does is, it is a reaction medium. It acts as a medium to transmit pressure. And some or all of your reactants, when your water is under pressure, then even if your reactants were not soluble under ambient condition, they would be partially soluble. So it aids the reaction. Okay, so what do we do is, this is how it looks like. This is a simple autoclave. This is your autoclave vessel, and inside you put it a liner. And autoclave vessel could be made of anything. Like mine has been made up of stainless steel. Inside I put a Teflon liner. In that I put my reaction mixture and then I seal it. And then it is heated externally. Okay, so we take the salts of the reactant, we transfer my reaction medium to Teflon lined autoclave, heat it at 100 to 200 for 1 day, 2 day, 8 hours, 10 hours, sometime over a week. Okay, and then you precipitate, take the reaction mixture out, centrifuge it, take out your precipitate, wash it so that the unwanted reactant or the byproducts, they go away, and then you get material. Advantages, you get defect free material. Different morphologies are possible. And again, one route, because whatever happens in earth crust is a very different condition. You are providing it, you are doing the synthesis under in water under pressure. So there is a chances that you would get crystalline modification that might not be possible by heating those material at high temperature. Advantages, okay, there are crystalline phases which are not stable at high temperature, but you want to get them. This could be one route because ultimately आप temperature तो ज़्यादा दे नहीं रहे हो. Okay, then you can also synthesize the material with low melting point. And because this is happening under hydrothermal condition, growing layer by layer, it creates larger size and high quality crystal. You can have controlled morphology and particle size, and you can also achieve difficult to synthesize phases. Limitation, you will have to buy autoclave. They come for price. Safety issues, if you have not designed your experiment properly, because ultimately a pressure is being created in your reaction vessel. Multi-component system like sol-gel synthesis, it was a good method. This might not be the best method, but still worth attempt. I'll give you an example of my own work that I did by hydrothermal synthesis. I wanted to synthesize layered zinc pyruvanadate. Now, this particular compound has a structure wherein you have ZnO6 octahedra, okay? And then those ZnO6 octahedra, they join by edges forming sheets. And such many sheets are joined together by pyruvanadate group. And what is the pyruvanadate group? This. Okay. And these OOO, they go into the zinc oxide layers that I just described. So these act as a pillar holding my layers together. So structure is somewhat like this, this. And these kind of structures are not possible. If I had taken my zinc carbonate and ammonium vanadate and heated it at high temperature, now what I would have got? I would have got this phase. And this is a simple crystalline compound with 3D connectivity, nothing important. But I wanted this layered compound only. Okay. So what I did was I mixed them together. I got a yellow precipitate. Of course, this pH, you will ask me, how did I get it? I wanted to precipitate a hydroxide of it. So I wanted high pH. And also in addition to that, you have to do a lot of trial and error. I got some precipitate, and that precipitate I put it in my autoclave at 120 degrees centigrade, and I got this material. Then I tried with what difference will it have on the morphology of my product if I heat it for different durations in my autoclave. So I did that experiment. This was after autoclaving it for 15 minutes. Some product I got, some morphology. Product was, let me tell you, for all four of them, the XRD was perfectly similar. After 30 minutes, it gave me this nice hexagons. Okay, this was the best product that I achieved after 2 hours. And after 5 hours, again that hexagonal morphology is there. But as you can see, my hexagonal particle have started breaking up a little. Okay, this was a very interesting experiment, and these are probably the best SEM that I have received for any of my products. Okay, so this is how we plan. I'll just rush up a little. Sonochemical. What is sonochemical synthesis? What happens is, in sonochemical synthesis, you take your reaction mixture and you pass sound waves through it. So what happens? Sound waves interact with your reaction medium and it generates hot spot. You can imagine them as some small bubbles. And those bubbles can achieve very high temperature of the order of 5000 Kelvin with very high pressure. They're very, very small. So pressure generated could be greater than 1000 atmosphere. And they burst immediately. So the rate of heating and cooling is like super fast, 10 per 11 Kelvin per second, order of that. What happens is in those bubbles, the reaction happens because those bubbles externally, your material is not being heated. When you provide sound wave to it, when we use our sonochemical vessel, externally the temperature goes only up to 70 to 80. But inside that acoustic cavitation or the formation of bubble occur, that leads to the formation synthesis of your material. Okay, so it utilizes the principle of sonochemistry to make molecules undergo chemical reaction with the application of ultrasound radiation. Okay, advantages, it permits synthesis on a bench top The sonochemical apparatus is a benchtop apparatus only. In room temperature liquid, that would otherwise have required high temperature, high pressure, or longer reaction durations. This is how it looks like. This is basically your setup. This is a titanium horn that actually moves to produce sound waves. This is your reaction path. Okay. And of course, based on the reaction, this is not of use to you. So let us not discuss that. This is just one example of sonochemical synthesis. I have not done it, but a colleague in my section only has done it. We took indium ethoxide, CTAP. Now, CTAP is a surfactant. I will not discuss any surfactant-based synthesis, but you might come across it. So just for your knowledge, surfactants are used. See, once your nanoparticles are formed in the reaction mixture, what will happen? They will be very active because they'll have large surface area. There'll be a tendency to coalesce and form bigger particle. So your purpose of getting nanoparticle would be lost. तो उसमें हम क्या करते हैं? We add surfactant. Surfactant covers your nanoparticle. तो जो वो cover करता है, it prevents the smaller particle to coalesce and grow together. So your nano remains nano. Okay, that is the purpose of CTAP. And there are many more surfactants that people use. So indium oxide and CTAP was taken in the solution at pH of 10 because I want hydroxide. We passed ultrasonic radiation and this product was obtained. This product was filtered, centrifuged, and washed and then heated. Upon heating, it gave indium oxide, nano indium oxide. So this is a TM of your indium hydroxide nanocubes, okay, which has the size of 30 to 35 nanometer. And when we further decomposed it, we got indium oxide, which is still smaller size of the order of 9 nanometer. Okay, again, an example of sonochemical synthesis. Advantages, you're getting your synthesis done at ambient temperature. ज़्यादा कुछ नहीं जा रहे हो. Reaction rate जो मिलते हैं वो बहुत ज़्यादा होते हैं and consequently time कम लगता है. Quick है, simple है. Limitations क्या है? Because acoustic जो cavities बनती हैं उसके अंदर बहुत high temperature और pressure जाते हैं. So we cannot have heat sensitive material. Scaling up is definitely difficult. Making huge ultrasonicator for synthesis is not that easy. Energy बहुत लगती है. That is one more drawback. Energy supply needed to carry out sonochemical synthesis is quite high. Therefore, if we take out the yield, we calculate the yield. That is amount of the product formed per unit of energy. That is low. But again, as I said, if you're going for high-end synthesis, you basically have to balance. मुझे क्या चाहिए, मैं किस application के लिए देख रहा हूँ, then you have to design your synthesis. Okay, simple pyrolytic. If you start with simply the acetates of the reactant, do nothing, okay, and then heat them at their decomposition temperature for various time durations, you will get oxide. And by maneuvering the decomposition temperature and the time of heating, we can actually get different particle sizes. Okay. Metathesis. Now, metathesis is one reaction which probably is very simple to imagine. You have a reactant AX and BY, they mix together and they swap partners. It's just that. You get AB and XY. Okay. And we do it simply in mortar and pestle. Mortar pestle mein we take two reactants and grind them. Grind it for an hour, 2 hours, 1.5 hours, 45 minutes, depending on the experience we get with a particular material. Simply take the entire reaction mixture and put it in water. Because one of the reactant, of course, it will not happen for everything, should be soluble. Okay. And so it will simply get solubilized in the water and I will get the other product would be, insoluble and I can simply filter it off. For example, I want to synthesize lead titanate. What I can do is I take lithium titanate, I take lead chloride, grind it, mix it. I will get lead titanate and lithium chloride. Put it in water, bada beaker of water, lithium chloride will solubilize. And I will be left with this. Wash it and this is your product. So it can be used for the suitable reactant. It is a double exchange reaction. What is the driving force? Why will it happen at all? Because the other salt that is being formed, no, this has high stability. Okay, so most of the time it is formed when your byproduct is alkali metal salt, alkali metal chloride, for example. So that is the driving force for carrying out this reaction in this forward direction. And we wash the soluble byproduct, as I mentioned. Molten salt flux. This was one synthesis that I did when I was doing my MSc project. This is nothing, simply solid state. You take your reactants, mix them in stoichiometric amount, and then you put it in a salt. Molten flux, what does that mean? Let me explain it to you. Flux means salt or the eutectic of the combination of salt, which will melt much below the reaction temperature that you need. Okay, so what will happen is, now you have at high temperature, you have a molten medium and your reactants. So your reactants have got high mobility, diffusion is much higher. So you need not go to very high temperature for synthesis. Okay, and then you ultimately cool it. That flux that you took, salt or the mixture of salt, you cool it and you put it in water. The salt will dissolve and you can separate out your product. Okay, so basically it uses salts or their eutectics which melt much below the reaction temperature. Reaction is carried out at the temperature, your salt should melt, of course, that is a criteria. It enhances diffusion, and because it enhances diffusion, it lowers the reaction temperature. Flux is water soluble and product is not, so you can separate it out. Okay, so the procedure is, we weigh stoichiometric amount of reactant. You also weigh the flux salt, because ratio of the reactant to flux is important. Most of the time we take it 50s to 50. Okay, now grind both the reactant and flux together, right? You have to homogenize them also, and then heat it at the temperature greater than the melting point of your flux. Okay, carry out the reaction, let the reaction cool and wash off the flux. Okay, so what does basically flux do? It increases your reaction rate and in turn it lowers the reaction temperature. It increases the degree of homogeneity because it allows more diffusion. It controls the particle size and shape, and because it is thick, it is viscous, it does not allow particles to agglomerate. It also controls the agglomeration state. Different kind of flux that have been employed are mostly chlorides and sulfate. I used this particular flux during my MSc synthesis, MSc project, okay. And these are the different flux we can use. And then if you ask me, why did I use a eutectic and why not simply NaCl and not KCl? I can use that also. Just that the eutectics, if you remember your phase diagram, okay, this is how eutectics look. The melting point of the eutectic is lower than the melting point of the constituent salts. That is why eutectics are chosen. Okay, just one example, exactly the work I did. Okay, so this is the same compound I tried to prepare by solid state route, and because solid state does not allow for good homogeneity, so despite multi-step process, I got two phases. This was carried out by salt flux, and this was done at 1100, this at 900. Single phasic product, lower temperature. ओके, प्रॉब्लम कहाँ आ सकती है? प्रॉब्लम आती है प्योरिटी में. कई बार आपके सॉल्ट आयंस इनकॉर्पोरेट हो जाते हैं प्रोडक्ट में. In that case, the way out is that you use the salt containing cations present in the desired product. For example, if I want to synthesize this complex oxide, I will take strontium fluoride flux. So this is a common ion, right? Even if it goes, I won't know where it has come from, right? From the flux or from reactant. Or you use flux where the cations of the flux are different in size as compared to ions in your product. Then it will not incorporate. Suppose I want to synthesize lead zirconate, big ions. You do it in B2O3 flux, small ions, it will not incorporate, not impure your product. Okay. Again, showing how it affects the morphology. This particular product is made by solid state route. And density, as you can see, is not very high. You have a lot of pores, the black things that you can see. This is obtained by flux route. The particle size is not homogeneous, but the product is dense and the morphology is much better defined. Okay. High pressure synthesis, won't talk much about it, just that what actually are you doing in high pressure synthesis? By applying pressure, you are controlling a fundamental parameter, and that is interatomic distance. And it is interatomic distance that controls the electronic structure, crystalline structure, and virtually all the interatomic interactions that determine the material behavior. So, because you are doing something which is the fundamental, you're tempering with something which is a fundamental property. So, there is a possibility that the crystallographically unfavorable compound can be synthesis. For example, in case of silicate, silicon cannot have a coordination number greater than 4. But under high pressure synthesis, a polymorph called stishovite has been synthesized, which has silicon in the coordination number of 6, because you compressed it. You literally ordered it to do so. Okay. So crystallographically unfavorable compounds are formed, thermodynamically unfavorable compounds are formed. And if you're tempering with the basic qualities, you can actually get exotic material, and synthesis of minerals is possible by using high pressure synthesis. Okay. Now, this is something that I wanted to discuss in detail, but for the lack of time, I'll simply tell you what is a combustion synthesis and then we'll wind it up. Combustion literally means combustion. You do it in my lab. We in a very funny way, we call it the fire and light show, basically. So what happens is, you take your reactant precursor in an aqueous solution. Fine, that you've been doing in many synthesis. What is so special? The special is, now my reactant precursor is nitrate. Okay, that is an oxidant, remember. And then I put a fuel in it. Okay, now when you will have a fuel and an oxidant, what will happen? Combustion. This is what I'm aiming for. So what happens is, for example, let me give you an example. I want to make gadolinium zirconate only. I take gadolinium oxide, dissolve it, put nitric acid, it forms gadolinium nitrate. I have gadolinium nitrate in the beaker. I add zirconium oxynitrate. Homogenize, I have two reactants, okay? And they have nitrates now. Then once I've got a soluble thing, I have to have soluble, very clear solution. That is a prerequisite, okay? Then I add any fuel of my choice. Generally, of course, later on, you would know which fuel to use for what. But most of the time, you can use any amino acid, and that fuel should be bidentate, okay? It should be able to form complexes. Okay, I can use, mostly I use glycine. You can use glycine, urea, hydrazine, citric acid, whatever you want, and any amino acid. Basically, it should have low ignition temperature. मतलब मेरा external temperature मुझे ज़्यादा नहीं लगाना चाहिए, and it should be good complexing agent. So I put glycine. What does glycine do? Glycine will complex my metal ions. By complexing, what is it doing? It is bringing my metal ions in close contact. Now they are homogenized. Okay, diffusion distance is drastically reduced. Now what I do is, it has complexed it. I simply slowly evaporate the water at 90 to 100 degrees Celsius. And once it evaporates, because if it was only salt, I would have got all the water is evaporated, I would have got powdered salt. But now, because glycine is there and it is complexing, once the water is evaporated, I get thick gel. Okay. Now I suddenly raise the temperature of my hot plate to 250 or 300, depending on the ignition temperature of my fuel. Here it is, for glycine 300 works. Once I do, now the fuel, and it has got nitrate with it in the solution, and it has reached its ignition temperature. So it will burn. Okay. Externally, I have applied only 250 or 300. But internally, when combustion happens for a few seconds, a very high temperature of the order of 1200, 1400, depending on amount of fuel, amount of oxidant, ratio of fuel and oxidant will reach. Okay. And because of those high temperature generated for very short interval of time in my beaker, my reaction proceeds. And I get either the product directly or the precursor to the product, which I can heat at slightly higher temperature to get the final product. So basically, the concept is instantaneous high temperature generation for very short duration of time. So this is a schematic. I take all the reactant, I evaporate, okay, I get a solution, I make it undergo combustion, I get an ash. Yeah, and every time the ash prepared product obtained after the combustion has to be calcined at 550 to 600. Why? Because it would have a lot of carbon from glycine. So that carbon has to be removed. You get nanopowders. These nanopowders could be the product themselves, or they could be precursor to the product which you can sinter to get desired dense pellets. Okay. So this was the combustion technique I just described you. Advantages, it is a versatile process. I mean, I use it only for gel combustion itself. I use it as I told you, once you know 2, 3 techniques, you can tailor your technique. I use it as a precursor technique. Like I don't want to go to 1500 to get my product. But if I do a gel combustion earlier, what will happen is even if I don't get the product, I'll get a powder which has got the mixing of the reactant in nano form and in homogenized form, so that once I heat them, I will need very low temperature to get the same product if I had started as compared to if I had started with my bulk or micron size powders, reactants. I get homogeneous product powder at low temperature, narrow size distribution, high surface area, and because the reaction is happening in like fraction of seconds, so metastable phases, kinetically stable phases can be obtained. This is how my solution looks like, and I evaporate it, get a gel, and this is called auto ignition. This is how it looks like when it burns in the beaker. Of course, whether it gets burned in the beaker also depend upon oxidant to fuel ratio that you have to tailor. If oxidant to fuel ratio is stoichiometric, you will get such kind of flames. I normally do in fuel deficient condition, because fuel deficient condition helps you to not achieve very high temperature. If you are not going to very high temperature, then your particle size will be smaller. So there are so many things that you need to tailor. I don't know, will not be able to cover all of them. But as I said, powder properties that you will obtain will depend upon the nature of fuel. ज़्यादा कार्बन है तो combustion sluggish होएगा. Sluggish होगा तो you'll have lower flame temperature. Lower flame temperature can have two effects. Okay, it will also be undesirable for product formation, but desirable for smaller particle size. So now you have to optimize how much fuel you want to have. Okay, so lesser carbon content will have higher flame temperature but bigger particle size. Product jaldi banega, particle size bada hoga. So nature of the fuel, higher carbon, lower carbon, as well as ratio of your oxidant and fuel. Okay. These are just a few examples. For example, this is oxygen by fuel ratio is increasing this way. This is fuel deficient. You got very much smaller particle size because your peak broadening is related to particle size. Broader is the peak, lesser is the particle size. So the fuel, okay, this is fuel deficient. This is stoichiometric when you can see the flame, and this is fuel rich. Okay, so in this order only, as the amount of fuel increases, your flame temperature increases. Flame temperature increases means particle will grow. Particle will grow, bigger grain size. Bigger grain size, narrow XRT planes. Okay. Morphology difference, of course. This is the kind of morphology you obtain by solid state for the same product. And this is what you have obtained by gel combustion. Much better packed product. Okay. Again, this is the microstructure of ceria obtained by, this is by gel combustion. This is by hydroxide, that you prepared hydroxide, cerium hydroxide, and then heat it to get ceria. This is you prepared cerium oxalate and then heat it. Okay, so see the difference in the morphologies. Okay, so I guess this is I told you I don't just use gel combustion for getting nano size. I also use it as a precursor for carrying different temperature synthesis at different temperature. Okay, and this is a beauty of it. I got precursor to gel combustion. They were all heated at 600. This table, I will not go into the detail, only shows by using a single precursor from gel combustion, which gave me a very, very homogenized mixture, and using different temperatures, I obtained different crystalline phases. Okay, same material, different temperature. How many phases I can tailor? Okay, so ion exchange, I would skip. We don't have time. So basically, what did we learn? To this class, we talked about probably one of the most fascinating branches of science, which is creation, right? And we know every synthesis route has got pros and cons. Your choice will depend upon what you want from it. Okay, what is application that you're looking for? Then, if you want to really go for a high-end application, choose for the synthesis route, which might involve different precursor, costlier reactant, costlier synthesis route, because your application demands that, isn't it? High temperature conventional synthesis is the most reliable route if you want to go for bulk production, phase purity, and thermodynamically stable product. You don't want any frill project. It's a no frill project, basically. No frill products ज़्यादा कुछ fancy नहीं चाहिए, then this is probably the most reliable route. You want to get metastable thing, you want to get nanomaterial, you want to control the morphology, you want to control the phase, then you would go for soft chemical route. If you come across this term in literature, this is shimidu. Shimidu means soft chemical synthesis, okay? Or you want to control all of this, why not combine this with this? Ultimately, your imagination only limits you, right? Proper choice of reactants and reaction parameters would be needed in whatever synthesis route you choose to. So basically, our endeavor is to control morphology for better materials, to control powder properties for better materials, and the structural behavior. This is all we need to do to get advanced functional material, which is your course is all about. Okay, so here we end my portion. We are left with two topics. We'll try to see where we can fit in with those two topics and finish my portion as well. Beyond this, I will stop my lecture for today. And you have any doubt, please feel free to write to me. Visit me if you are in BRC or wherever. I would be happy to. Sure. The PPTs would be shared. PPTs would be shared. No, Anurag, they would be shared, yeah, with the students. Anything pressing that you need to ask, please do that. Otherwise, we'll close the lecture. We've already crossed our time limit today. I will just see the chat box and then find it. Okay. Okay, thank you very much for all your patience with me. And I wish you all the best. We'll anyway meet for one more lecture, but that we'll see how to fit in. And good day to all of you. We'll wind up here. Thank you.